All right, this is sample problem 3.1 right from your textbook, and I just want to verbally walk through it in a video for you. So here we have this shaft here, OA, right? It's a lever. So the lever is attached to some shaft at O. So determine the moment about O, and you're given that this has a 100-pound force acting at this point A directly downward. So we want to know the instantaneous moment, right? Because as the shaft turns, this angle is going to change. And you want to know a few things. So we're going to learn that. Then we'll find the horizontal force at A that creates the same moment. So up here at A. The smallest force at A that produces the same moment. And the location 240-pound vertical force to produce the same moment. So here we have 100 pounds, right? Where would we put a 240-pound force, vertical force, to create the same moment? And then are any of the forces from B, C, and D equivalent to the original force? So let's walk through this. So let's first find part A, right? And all these are basically asking for the moment, right? And we're going to be using this basic formula. The moment is the force times the perpendicular distance from the point you're looking for the moment about, right? So for example, this 100-pound force is acting downward. The line of action of this force, right, the perpendicular distance from the point of origin is from the line of action of the force, right? So we look at the line of action of the force, and where's that perpendicular? Where's that perpendicular distance to the point of rotation? And here you can see it's basically, and they give you, right, they give you the hypotenuse. So it's 24 inches is the hypotenuse times cosine 60. Remember, cosine is adjacent over hypotenuse. So we're interested in this adjacent distance D. And so we wind up with the moment is minus 1,200 pound inch. So again, note your units. A moment is a force times a distance. So in this case, it's pound inches. You could convert the 24 inches to 2 feet, and instead of let's see, what do we have? We'd have 1 foot, so you'd have 100 foot-pounds, right? So you just basically divide this by 12. So you could have pound-foot, which would be 100-pound-foot, or 1,200 pound inch. Notice the direction of this. The direction is clockwise. So the notation we use for the moment is negative. So you would either report this as a negative 1,200 pound inch, or you report it as a 1,200 pound inch with an arrow showing the direction of rotation. All right, part B. The horizontal force at A that produces the same moment. So now we're looking, we want to apply a horizontal force that produces the same 1,200 pound inch moment. So now we know, let's see, we know we want the force horizontal, and we're going to have to solve for the distance here. So notice now we're looking at the vertical distance. So if this is a triangle, 24 inches is the hypotenuse, right? The distance from the perpendicular distance from the origin to the line of action of that force is the height of this triangle, D, right? So it's sine, right? Sine is opposite over hypotenuse. So the opposite side, right, over the hypotenuse. So sine 60 is opposite over hypotenuse. You should be able to rearrange it to get this. You see that the distance is 20.8 inches. We want to know the force, right? We know the moment. We know we want a 1,200 pound inch moment. We solve for the distance geometrically, and now we just rearrange those to solve for force. And we see that the force we need is 57.7 pounds acting horizontally. So notice this, right? We had a vertical force acting this way of 100 pounds. If we act, so the vertical force was at a short distance, right? Now we've increased the distance from the line of action by going horizontally, so we need less force to generate the same moment. Oh, why must the direction of this F be to the right? Why don't you pause this and think about it? All right, hopefully you're back. Well, the moment, right? The moment we wanted to generate was in the clockwise direction. So this means that we need to have, if it's going to be a horizontal force, right, we have two options, to the right or to the left. And to the left is going to generate an opposite moment, right? It's going to generate a counterclockwise moment. All right, here's something to think about. Why is the smallest force at A, or sorry, what is the smallest force at A? What is the smallest force at A that produces the same moment? So pause the video and think about it. And think about where that smallest force would be and how you'd get it, or what that force would be and the direction. All right, hopefully you're back. The smallest force at A to produce the same moment. Now notice here, right? Remember, our moment is going to be clockwise. So this arrow is not going to work for us, and neither is this arrow. This is going to pull it counterclockwise. If we start looking at this, we had an arrow of 100 pounds pointing straight down. We looked at a horizontal arrow, right? As you change the angle here, what are you doing? You're changing the distance from the origin. Let's see. So the smallest force is that at the greatest distance, right? And the greatest distance is going to occur between the origin and the line of action when F is perpendicular to it, right? You can see here, right? If the line of action goes this way, right? Our perpendicular distance from O to that line of action becomes smaller. We want the distance to occur, or we want the force to be the smallest, so we want the distance to be the greatest, and that's going to be when it's perpendicular. So here we have a 1,200 pound-inch moment. That's what we want, and we're trying to find the force. The minimum force is going to occur when it's perpendicular to the origin along this lever, right? So that's 24 inches. This is the maximum distance we can get from point A to point O. With a force's line of action. And that becomes 50 pounds. So 50 pounds is the smallest force you need to produce the same moment, and it has to be acting perpendicular to the shaft of the lever arm, I guess. All right, part D. Determine the point of application of a 240 pound force to produce the same moment. So now we know that we have a moment of 1,200 pound-inch this way, right? It's 100 pounds here. We want to find, or that's produced by 100 pound force. We want to find where would we put a 240 pound force along this length to give us the same moment. So obviously we've got a higher force, right? We can get a smaller distance. So we can put this closer to the point of origin. And the question is where is it going to be close to? Well, so again, we use geometry to just find we define an arbitrary distance d. We know our moment. We know the force we want. Now we got to solve for d. D is 5 inches. But then where along this lever do we put it, right? So we're looking at a triangle now where D is 5 inches. We want to know what the hypotenuse of that triangle, OB, right? So OB cosine 60, right? Hypotenuse times cosine 60 is the adjacent value. So we just get OB is equal to 10 inches. So a 240 pound force has to be 10 inches from the origin at the lever applied straight downward to give us that same 1,200 pound-inch force that 100 pound gave us at A. Remember, this is a 24-inch lever. All right. So remember, parts B, C, and D, we produce the same moment as the 100 pound force, right? We had the 100-pound force at A, we had a horizontal force that we figured out. We had a perpendicular force that we figured out. But notice here, none of these are the same magnitude and sense or same line of action, right? So the forces are not equivalent, right? All the forces are different, but we wind up with an equivalent moment. So you can get the same moment by applying different forces at the same point along different lines of action. So I think the point they want you to think about here is what I just said, right? Various combinations can produce equivalent moments. And the system of a force and a moment produce a different overall effect for each case, right? Yeah, so that's sample problem 3.1. Thanks for watching.